Welcome to Design Multi-Campus Layer 3 Infrastructures. This is domain 2.3 on the ENSLD blueprint. If you've been working your way through ENSLD, then we've already taken a look at routing protocols, and we've now taken a look at Layer 2 campus designs. But now we need to look at large Layer 3 enterprises. When we think about deploying a routing protocol to a small network, like let's say we have 4 different Layer 3 nodes, well, sure, we just deploy OSPF or EIGRP and life just takes care of itself. But when we talk about these large enterprises, we scale out to hundreds or maybe even thousands of Layer 3 devices in the network. Well, now all of a sudden, we don't want one small change or one small hiccup on one end of the network to ripple through the entire infrastructure. So we have to think about ways that we can converge fast and also absorb changes in the network. So come along with me. We have a lot of fun exploring how we handle this in large Layer 3 networks. And with that, I will see you in the next video. Routing convergence, summarization, and filtering. That sure sounds like a lot to cover in one video. And maybe a better video title would have been Layer 3 Scaling, because that's really what this topic is supposed to be covering, is how we scale out for large Layer 3 networks. But if we look at the ENSLD blueprint, it calls out convergence, summarization, and filtering. So regardless of how we want to call it, our focus here is thinking about building a network with hundreds or thousands of Layer 3 nodes, and making sure that a network that size is robust and can converge very quickly in the event of a failure. Let's take a look. Let's start by looking at convergence. If we have a problem with one of these links, let's say this link goes down, we want to detect that failure as quickly as possible. Now, if this is a copper connection, then the routers on each end are going to realize that the electrical circuit has gone down. However, if it's a fiber optic connection or we're going through a switch in the middle, then we're not necessarily going to know that that connection has gone down quickly. This is where the concept of timers comes into play. OSPF, EIGRP, any routing protocol is going to have timers that let us know that, hey, I haven't gotten a message from the other side in a while. Maybe it's time for us to take this connection down. But there's a problem with those timers, and that's that by default, a lot of timers exist in the 10-second to maybe even up to 40-second range, depending on our routing protocol. And we don't want to have to wait 10 to 40 seconds to realize that we need to do something with the fact that this connection has gone down. Now, most routing protocols allow us to tune those timers down into the millisecond range, and that sounds good at first glance, but then we realize that these packets have to be processed by the router CPU, and so if we're sending it millisecond timer intervals, well, that's going to make our CPUs very, very busy. Now, if you're working your way through the ENSLD course, then you recall, as part of the high availability conversation, that we can use the bidirectional forwarding detection, or BFD protocol, instead of relying on routing protocol timers. This is the preferred method. We want to make sure we're leveraging BFD for our routing protocol connections and leave the routing protocol timers alone. So this is going to really help us from detecting a failure perspective, but now we have another problem. Because now that we've detected a failure, now we have to report that failure to the rest of the network. And a small failure, let's say a network going down here at the very edge, propagating to everywhere in the network, well, that's going to cause a problem as much as anything, because the more sites that we have, the more likely there is to be a problem. If we have a large enterprise network, again, of thousands of routers, well, we might be dealing with small failures every single day throughout the network. And so as these small branch sites start to have issues for one reason or another, well, that can cause a ripple effect throughout the network. Instead, it would be great that if we have a problem, let's say at this branch site here, that we somehow absorb that change to the rest of the network. And we have a couple of different ways we can do this. First of all, we have this concept of stub routing. This is particular to OSPF and EIGRP, which have stub configurations. One of the key benefits of stub networks is that if there are changes made within a stub area, then we don't necessarily need to propagate that through the rest of the network. Now, the way OSPF and EIGRP do this are different. For example, OSPF uses the concept of route advertisement within the stub area, whereas EIGRP's primary benefit has to do with that query concept. We're not going to query stub sites for a route that goes into an active state. However, there is another way that we can absorb changes to the rest of the network, and that would be with summarization. The idea of route summarization says that let's say I have a router here at the edge and we've got 4 different routes attached to this router. Rather than advertising all 4 routes upstream, what if we were to advertise one supernet upstream to the rest of the network? So maybe we have 4 different /24 networks here, and instead we're going to add a single /22 network. If we do our binary math and our subnetting knowledge comes into play here, we know that a /22 consists of 4 different /24s. And so by advertising a /22 into the network, we're giving the network the exact same amount of information, but at the same time, less routes and a little bit less detail. For example, if one of these networks were to go down for any reason, maybe it's a maintenance update, or maybe it's a link to a downstream router that goes down. Either way, if we lose that connection, we don't actually have to advertise that to the rest of the network. Instead, the /22 continues to be advertised, and the rest of the network is none the wiser. Normally, we would have to advertise out, hey, that network went down, and then that network needs to be advertised everywhere to say, oh, that network went down, that network went down, right? We don't need the entire network to be converging around the concept that this one edge route went down. On top of absorbing changes, we just took 4 routes and summarized it down to 1. And if we were to do this with all of our routes, then the core routers, the routers here in the middle, are going to have 25%, 1/4 of the number of routes that they would have had otherwise. This saves on routing table space, so our routing table size has gone down, and that might even mean that we need a less powerful router. This could save us money when we're doing our network designs. But speaking of designs, we need to make sure that we design our IP addressing space to facilitate summarization. Because if these /24s aren't adjacent to one another, then I can't use a single /22 to summarize them. So for example, if I were to assign 10.0.0.0/24 to that network location, then I want to make sure that the next 3 /24 blocks are contiguous with this block. For example, that would be 10.0.1.0, 10.0.2.0, and 10.0.3.0. If, however, I assign 10.0.0.0 to this location, and 10.0.1.0 to this location, and the next one down here, and the next one down here, well, I can no longer summarize that block. So I need to be very intentional with how I design my IP addressing scheme to allow for summarization in the network. Now, one key point to make in summarization is that this is primarily used in distance vector protocols, meaning specifically RIP and EIGRP. You say, well, wait a second, Jeff, why can't we use this in OSPF? Well, we can use it in OSPF, but with a big caveat. When we're talking about link state protocols all share a database. And the funny thing is that when we talk about summarization is a little bit deceptive. In our example up here, I'm not telling the upstream routers that I actually have 4 routes. I'm telling them I have 1. That's a little bit of a lie, right? But if we're going to have a shared database among all of the routers in a particular area, I can't lie to my neighbors. They need to have exactly the information that I have in the same way that I need to have exactly the information that they have. So with distance vector protocols, I'm able to summarize router to router because it's a trust-based relationship. I just trust whatever you tell me, which ironically allows me to betray that trust and tell you something that's not quite true. But with a link state protocol like OSPF, the only place that I can perform summarization is between network areas. That's because once we cross from one area to another, we're back to that distance vector trust-based relationship. I'm just telling the other area whatever it is I want to tell them about the area that I'm coming from. Now, this is a topic that can be a whole lot deeper and take a whole lot more time to study and think about. But the key point to take away here is that when we're talking about link state protocols, summarization can only happen at area boundaries, whereas with distance vector protocols, we can summarize readily between routers. Now, last up is the concept of filtering. Filtering is not a technique we're going to use too often. However, it is a tool in our belt that we need to be aware of. The idea of filtering is to simply negate a route on a particular router. Now, this can be in the ingress direction, or it can be in the egress direction. In other words, I could have a bunch of routes behind this router here, but when I advertise upstream, I could summarize these, sure, but I can also filter. I can just say, you know what, I've only got 3 routes. This would be an egress route filtering concept. Meanwhile, if routes are being advertised, let's say I have a bunch of routes here and all of them are being advertised upstream, I could filter here and say, you know what, I don't want all of those routes. I'm only going to take the routes that I want. Route filtering is accomplished in configuration with something we call a distribute list. And the distribute list will tell the router which routes to accept when it's on ingress, and by the way, which routes we want to advertise to our neighbors on egress. But this same concept that we just talked about summarization applies to filtering as well. From a distance vector protocol, I can tell the upstream router whatever I want and they're going to believe me. And likewise, when the routes are coming in, I can selectively take which ones I want. But when it comes to link state, we don't really have that luxury. Again, a shared database among all of the routers in an area means that we all have to have the same database. So we cannot filter routes to one another because we're really not sharing routes so much as we're exchanging database information. However, link state protocols do allow us to do ingress filtering, keeping in mind that we're still sharing the same database with everyone. So, our brains want to go to distance vector and say, well, as I receive a route, I'm going to filter it, and therefore I can't pass that route on. Well, in link state, that's absolutely going to happen because I'm still sharing all of my LSAs with all my neighbors. So I'm not blocking that route from being shared with anybody else. However, I can use ingress route filtering to prevent that route from being installed into my routing table. Meanwhile, by the way, with distance vector, if I do an ingress route filter and I don't have that route, well, I can't pass that upstream to my neighbors, and so I'm effectively filtering that route from reaching any of the upstream network. Anytime we're talking about route manipulations, we have to really separate the concept of distance vector and link state in our minds. They're going to behave very differently from this perspective. Now, there aren't 1,000 use cases for route filtering out there. Really, it's just a tool that we have for that unique situation that's going to come up where we have a route, let's say route A on this router here, and we just do not want that router to have that route for whatever reason. So whether we're using ingress route filtering on one side or egress filtering, if that's applicable, regardless, we have the power to get rid of that route from our routing tables. So when we're designing our layer 3 networks, we absolutely want to take advantage of these route manipulation techniques to scale out in a robust fashion. First of all, we think about convergence, failure detection. We absolutely want to use BFD. We don't want to tune timers because that's going to increase CPU cycles on our routers, and BFD helps us converge faster anyways. Second of all, we have summarization. Summarization is able to absorb any small changes that are, throughout the network, small routes or edge routes going down. We don't want to necessarily propagate that through the network, and so summarization absorbs those changes, but also reduces the routing table sizes on our core routers. Next, we have route filtering as a tool. Flat out, route filtering allows us to get rid of a route on a local router. But hey, with route filtering and summarization, we absolutely need to keep in mind through all of this that link state and distance vector, they behave very differently. So let's make sure that when we're doing our route manipulation designs, that we take into account whether we're using link state or distance vector. And hey, depending on the scenario, that might even impact which type of routing protocol we choose between EIGRP and OSPF. I hope this has been informative for you. I'd like to thank you for viewing. The ENSLD blueprint calls out load sharing, which to most of us, that's really talking about load balancing. But in the layer 3 world, it's a little bit different compared to what we do with layer 2, which is to form an ether channel or port channel and rely on hash-based load balancing. In layer 3, yes, we can create ether channels, but we can also load balance without ether channels because our routing protocols allow us to install multiple routes into a routing table. In this video, we're going to explore all of the elements of how we do load sharing and load balancing from a layer 3 perspective. Let's take a look. When we're running a routing protocol, let's say in this environment with 4 routers, and they're all sharing routes with each other, it's not an uncommon situation for us to realize that we have 2 equal cost paths out to a particular destination. As long as I'm receiving routes and populating in my routing table multiple routes that have the same administrative distance, in other words, they have the same routing protocol source, and they have the same metric, whether it's an EIGRP metric, an OSPF cost, or what have you, either way, if they're the exact same, then they're going to both get installed into the routing table. So in our example here, this router here on the left, let's call this router 1, has 2 different equal cost paths to get to the subnet on the right. By default, Cisco routing platforms support up to 4 different equal cost paths to be installed into the routing table at once. But depending on our platform, we can actually increase this to up to 16 or maybe even 32, depending on the platform, different equal cost paths that can be installed at the same time. We call this concept equal cost multipathing, or ECMP. Now, depending on where you are in your CCNP journey, you may have already studied the fact that EIGRP has a pretty cool feature, and we call it unequal cost multipathing. We can use the variance command in EIGRP to support installing multiple routes into our routing table, even if the costs aren't the same. For example, if in our scenario here we had a metric of 2,000 on the bottom and a metric of 1,000 on the top, well, without unequal cost load balancing, we would prefer the top path in every given situation. However, as long as the bottom router is a feasible successor from an EIGRP perspective, then configuring the variance command will allow us to leverage that second link. And effectively what we're going to do is we're going to load balance, but from an unequal cost perspective. So ideally, if everything works out well, we're going to be sending 2 packets out the top link for every packet that we send out the bottom link. And that's because the primary link is roughly twice as good as the secondary connection. Now, while unequal cost load balancing is a cool concept, in most scenarios, we're going to be dealing with a network that is based on equal cost multipathing. And so the question is, how exactly do we load balance across equal cost connections? With ether channels, we are accustomed to using a hashing algorithm to determine which link we should use in a given scenario. And by leveraging hashing, we actually accomplish 2 separate goals. First of all, appropriate load balancing. We want to maximize the utilization of both of those links. We always imagine that if we're ether channeling across 2 connections, that they're at a 50-50 ratio from a traffic perspective, but that's almost never the case. Our goal is to get as close to 50-50 as possible and stay away from a scenario where maybe we're 90-10% load balance. That would be pretty bad. But the second goal that we have that isn't often considered is the idea of keeping a flow on a particular link. If we're sending traffic across an ether channel between 2 switches, for example, when a networking device initiates traffic and starts putting a network flow onto the switch, the goal here would be for us to pick one of these links, let's say the top link, and send that connection across to the other switch. And every packet that comes in on that network flow would continue to use that same link. The reason for this is to prevent out-of-order arrival of the packets on the other side. We want to make sure that we're not introducing jitter into the mix. We want to make sure that our packets are not arriving out of order. Now, when we're doing layer 3 load balancing across two different links like this, we're not going to be using ether channeling, but we still want to accomplish the same two goals. We want to equally load balance across those links, and we want to keep our flows in sequence if possible. Unfortunately, it can be difficult to accomplish both of these at once, which is why Cisco gives us two different options for load balancing from a layer 3 perspective, with a focus on either load balancing or flow-based operation. The default behavior for a Cisco router is to do per destination load balancing. The focus of this load balancing operation is to favor flow-based control. We want to make sure that our packets are arriving in order. So as the packet arrives on router 1 up here in the diagram, it's going to look at the destination and it's going to assign that destination to one of the two links. So as packets continue to come in for that destination, we're going to be putting that on the same link. Let's say it's the top link up here. Now keep in mind that this does help a flow stay on a particular link, but this isn't per flow load balancing. In other words, we might have 100 different sources out here that are sending to a single destination, and all of those flows will be placed onto the same link. This can be problematic if we only have a few destination hosts. Let's say that most of the clients in our network are targeting a single server, let's say server B over here. If that's the case, as those packets are coming in destined for server B's IP address, well, a lot of those are going to be placed onto the same link, and so we might end up with that 90-10 load balancing situation that we described earlier. If this is the case and we have a problem with load balancing in our environment, then we can switch over to per packet load balancing. With per packet load balancing, we're going to be focusing on the balance of our link utilization. But per packet load balancing isn't perfect either, because if we have a single client, let's say A1 over here, that's sending out towards server B, well, every other packet in that sequence is going to get load balanced out a different connection. Depending on network conditions, this can result in those packets arriving out of order, which isn't a big problem with a lot of TCP-based operations, but it's a huge problem with voice over IP and other applications that are very sensitive to in-order arrival of packets. So while neither option is perfect, we do tend to see that per destination load balancing is a best fit in most scenarios. And that's mostly because in most networks, we're going to have a lot of destinations. And the more destinations we have, the better load balanced our links will be. Furthermore, we can handle more network types. For example, voice over IP works fantastic on per destination load balancing. If, however, our network conditions are such that we have very few destinations and our link utilization is unacceptable, then that's when we can explore per packet load balancing, knowing that it does come with those disadvantages. If we do decide that we want to change this, we would use the IP load sharing command on iOS routers. So when we think about load sharing, what we're really saying is that we can install many different routes into our routing table. In fact, up to 4 by default is supported, as long as the administrative distance, in other words, the routing protocol, is the same, as well as the cost to get there. Now, EIGRP does support unequal cost multipathing as well, so we can use the variance command for that if we're using EIGRP. Now, when it comes to deciding which link to use, we have two different choices. We have per destination load sharing, and that's usually what we're going to want to land on. It's focused more on delivering packets in order than it is on perfectly balancing our links. Now, we do have per packet load balancing as another option. We have to be very careful with this one, because even though it does focus a little bit more on link utilization, it's not good for in-order arrival of packets, and some network traffic, like voice over IP, is going to be very negatively affected by that forwarding option. I hope this has been informative for you. I'd like to thank you for viewing. Route redistribution is the topic of a lot of lab scenarios. It seems like we study this a lot in CCNA, CCNP level, and especially CCIE level. But when exactly are we going to use this in real life? Well, believe it or not, it can happen quite a bit. For example, if we're going to migrate from one routing protocol to another, we might not be interested in doing it all at once. We might do it halfway, and at that point we need to redistribute. We might acquire another organization. If we acquire an organization that's running a different routing protocol, and we have to interface with that organization's network temporarily until we migrate them to the protocol that we want them to run. And probably the most common scenario, though, is going to be that when we interface with a service provider, and that service provider wants to run BGP to us. That's pretty common, especially in the MPLS space. And so we do see this in real life, and it's very important that we understand not only how we configure route redistribution and what it's all about, but also what the pitfalls are, because we can't accidentally introduce routing loops if we're not careful. Let's take a look. Let's say that these 4 routers here in the middle are all running one routing protocol. Let's just say that they're running EIGRP. Next, we install this router here on the right, and maybe this router isn't a Cisco router, and so we can't run EIGRP, and so we deploy it with OSPF. And we have to let the rest of the network know where B is, and conversely, we have to let this router know where the rest of the network is. And the only way we're going to be able to do that is by forming an OSPF relationship between these two routers. But even once we formed an OSPF relationship, we still have a problem, because EIGRP routes aren't going to automatically get injected into the OSPF domain, and neither are OSPF routes going to get automatically injected into the EIGRP domain. This is where the concept of route redistribution comes in. This router here in the middle, the one that's running two different routing protocols, is going to be able to take those routes, not automatically, but when we manually configure it to do so, we're going to take those EIGRP routes and inject it into the OSPF domain. This is known as one-way redistribution. We're taking routes from one domain and injecting them into the other. Now, in most cases, that's not going to be good enough, because it's great that this router over here, let's just call this router 5. Router 5 now knows how to get to the rest of the network, but the rest of the network doesn't know how to get back to router 5. And so in that case, we need two-way or mutual redistribution. We need to take those OSPF routes and inject them into the EIGRP domain as well. At this point, life should be pretty good. All of these routers are going to know where route B lives, and the router here on the right, router 5, is going to know where A lives. Whenever we have a single source of redistribution, the topology usually ends up pretty simple. But things get a little more complicated when we have two different places where we're redistributing. So let's try this out one more time, but this time let's assume that our EIGRP domain looks a little something like this, only encompassing the 3 routers on the left. Meanwhile, let's assume we're running OSPF on the 4 routers on the right. So this is now our OSPF domain. It's a lot larger than it was before. And now we find that we have 2 different routers that are capable of redistributing. So the question is, which one do we want to redistribute on? And the answer is usually both from a redundancy perspective. Because if we do mutual redistribution on the router on the top, and that router on the top goes down for any reason, well, it would sure be lovely to have a second path forward. And so usually we're going to perform mutual redistribution on both of the routers in the environment. But now we have a little bit of a conundrum, and let me show you why. Let's look at the router on the top. It has an OSPF route pointing to B. We know where B lives. It's out our OSPF domain. Next, it's going to redistribute that into EIGRP and tell its neighbor, hey, I have a route to B. Except this neighbor is going to receive that as an EIGRP route, which is designated by D in the Cisco routing table. So EIGRP, route to B, perfect. So I let my downstream neighbor know, and now my downstream neighbor has a EIGRP route pointing to B. But this is interesting. Now we're going to redistribute that back into the OSPF domain. And the OSPF domain now sees that I've got a route down here. So while this router here is advertising and saying, hey, I know where B lives, well, all of a sudden, so is this router. This router is saying, I have a route to B. This is where we can form routing loops if we're not careful. We have to be extremely intentional with how we configure mutual redistribution on multiple points in the network. Now, there are 2 primary ways of dealing with this conundrum. The first of which is going to be administrative distance. Administrative distance does us a favor from the perspective that if our external routes are a higher administrative distance than our internal routes, then most of these problems are going to solve themselves for us. And EIGRP does this on its own. If you've ever wondered why EIGRP has a higher administrative distance on its external routes, in other words, internally we have 90 as our administrative distance, but externally we use 170. And this is the reason why. Because if we look at this router down here, now we have an EIGRP route, except that EIGRP route, having been redistributed into EIGRP, is going to show up with an administrative distance of 170. Meanwhile, we have OSPF on the other side, and OSPF has an administrative distance of 110. We're wired in our brains to think that OSPF loses to EIGRP because 90 is less than 110 when you compare internal administrative distances, but an EIGRP external will lose to OSPF. And this is the reason why we want it to lose to OSPF. So fortunately, in the scenario that we've diagrammed out here, this isn't going to be a major issue. However, what if we replace EIGRP with a different routing protocol that doesn't have the administrative distance split? What if, for example, we're running RIP? And RIP is simply a 120 administrative distance regardless of internal versus external metric. Well, OSPF doesn't do us any favors. Even though it tracks externals differently, it maps those to 110 just like it does with internals. So it's the same administrative distance on both sides, and now all of a sudden this router here in the middle is now hearing that, okay, I can get to network A via RIP, that's 120, but assuming it's been redistributed at the top, it's going to be hearing from OSPF that I can get out towards the OSPF domain. And my route to A here is 110. So it can be extremely problematic for us if we don't use different administrative distances between external and internal routes. As long as one side is doing that, we should be fine. So in the case of this scenario, with OSPF, we would want to migrate our external administrative distance to something higher than RIP. So maybe we just call this 150. If we were to do this, then our problem would be solved, because our redistributing router would see the RIP route as 120, but now it would see that OSPF external route as 150 instead, and so it would know to use the local path. So to summarize this, if we want to use administrative distance to solve the routing loops for us, we need to make sure that our external routes have a higher administrative distance than our internals. And that really only needs to be configured on one side, so if we have EIGRP and OSPF like we diagrammed, life should be good. but we could always go in and do something like this from an OSPF perspective just to be safe. Now, we do have one other solution for this methodology, and that would be to use route tagging. Every route that is shared within any routing protocol can carry a tag that remains associated with it throughout the life of its advertisements. In other words, me knowing about B from an OSPF perspective, when I advertise this into the EIGRP domain, I can assign a tag to it. So let's say we tag this route. Let's just pick a value of 110 to represent OSPF routes. Now, tag in no way changes the way that a route is perceived from an administrative distance or a cost perspective. It's simply a cosmetic change to the route. So now, as that route gets advertised, it maintains its tag of 110. And what we want to do on this redistributing router is to block redistributing routes that have a tag of 110. In other words, if I learned this route from the OSPF domain, I don't want to advertise it back into the OSPF domain. Likewise, as I advertise EIGRP routes into OSPF, I might tag that as 90. Now that I've got that tag associated with it, as that gets propagated via LSAs, now my router on the bottom is going to think about advertising that route into the EIGRP domain, except it gets filtered because I'm looking for a tag of 90. And I don't want to redistribute any route back into the EIGRP domain that has that tag. Now in this diagram, I've placed the tagging on top and the filtering on bottom, but really we would be doing both on both routers. We'd be tagging routes that we learn from one domain into the next domain, and we'd also be filtering at the same time. Even though administrative distance is effective at preventing routing loops, tagging is absolutely the best way to very intentionally configure and tune our network to prevent those loops from occurring. We are explicitly denying the advertising of a route that we learned from one domain back into the domain from which we learned it. This cannot happen when we're doing tagging and filtering. So sometimes it's best, even in a scenario where we are covered from an administrative distance, to consider deploying tagging in sort of a belt and suspenders model. If the administrative distance for whatever reason fails us, then we've got tagging to fall back on to keep us from introducing routing loops into our environment. Okay, now I do want to step back and place some minds at ease, because the conversation that we've just had around route redistribution and loop prevention, that's almost a CCIE level topic and is absolutely something that you'll study in depth if you go for the CCIE. But for the sake of the ENSLD blueprint, let's just keep a few things in mind. First of all, redistribution is what we would use to enable the sharing of routes among routing protocols. And number two, if we're redistributing from two different points in the network, that can introduce routing loops, and those are dangerous. So we do have two primary ways of preventing that. First of all is administrative distance. Administrative distance needs to be configured such that the external routes, at least on one side of the redistributed domain, the external routes have to be a higher administrative distance than the internal routes. And again, EIGRP does this for us. And so in a lot of cases, this is resolved before we even have to do anything manually. Now, it is usually best practice to still consider route tagging, even if we're relying on administrative distance. That's great. But tagging is a final, we absolutely cannot inject routes in a loop if we're using route tagging. So we consider tagging routes as we advertise them into a domain, and we filter that same tag as we are injecting routes back into that same domain. This makes it so there's no way we can accidentally share routes back into a domain that we learned from it. I hope this has been informative for you, and I'd like to thank you for viewing. Virtual routing and forwarding instances might sound a bit intimidating at first, but the reality is that VRF is simply a VLAN for routers. We're going to take a physical router, a physical layer 3 device, and carve it up into multiple virtual layer 3 devices. Let's take a look. Once upon a time, we had physical layer 2 switches, and if we had multiple clients connected to this physical layer 2 switch, but we wanted to segment these into separate broadcast domains, well, the only thing we could do is deploy a second physical switch. And we could swing this client over to the second physical switch, but eventually that got a little cumbersome, and so somebody really smart decided to invent the concept of a VLAN. The VLAN, or the virtual LAN, effectively carves up our physical layer 2 switch into multiple virtual layer 2 switches. So this is one broadcast domain, and this is another broadcast domain. And we're going to use a very similar concept with a VRF. With a VRF, we're going to take a router, and we're going to carve it up into multiple virtual routing and forwarding instances, otherwise known as VRFs. Each one of these virtual routing instances has its own routing table. In other words, the routes that are installed into the one routing table are not going to be installed into the other routing table. We do not route between these VRFs while staying on the box. This is very similar again to our layer 2 world over here, the layer 2 VLAN concept. Even though we know with multi-layer switching, we're able to route between VLANs by deploying SVIs. That's great, but we don't have a higher layer to go to from a routing perspective. Now, we do have a concept called VRF route leaking, where we can share routes between two VRFs, but in most of our designs, we want to stick to how VRFs were intended to function. So if we want to route between these two instances, then we're truly going to have to connect a cable between the two, and then we'll be able to route across it. At this point, we essentially have router 1A and router 1B. And so we can draw this out logically by showing an actual router. Router 1A with a physical connection to a different router, in this case, router 1B. Now, as mentioned, we have separate routing tables on each one of these routers. That's essentially the mark of a VRF. In order to populate these routing tables, we need to install layer 3 interfaces into each VRF. Once we start configuring VRFs, we're going to find that each interface is part of the default VRF by default. So if I wanted to create a VRF called R1A and a separate VRF called R1B, well, at this point, I technically have 3 VRFs on my router. I have the default VRF, I have R1A, and I have R1B. These are my 3 different VRFs. Once I've created these VRFs, I would start to assign interfaces into them. For example, I might take gig 0/0 and assign it to R1A. Meanwhile, I might take gig 0/1 and assign it to R1B. Every interface can only be assigned to one VRF. We cannot assign an interface into multiple VRFs. That does not work. That said, we can use subinterfaces to get around this from a physical perspective. So we could have a gig 0/0.1 as part of R1A, but then we could do a gig 0/0.2 and assign that to R1B. Every distinct layer 3 interface has to be assigned into one VRF. And yes, that does count subinterfaces and loopback interfaces and any kind of layer 3 interface. So how are VRFs used in network designs? Well, for one, from a service provider and a multi-tenancy perspective, this can be very useful, because we can take one physical device, carve it up into multiple logical devices, and assign those logical devices to our different tenants. However, for those who don't work for service providers and multi-tenant infrastructures, we're still going to find that there are places where VRFs show up. One of the most common use cases is going to be the management VRF. A lot of Cisco devices by default these days will have a dedicated management port. The management port might be on one side of the switch, and then we have the front-facing interfaces that face out towards the network. And this management interface is going to connect to the management network, and it will be part of a separate VRF. By placing this interface into the management VRF and placing the front-facing ports into the default VRF, well, now there's absolutely no way to route between the management interface and the front-facing ports. The only way we could do that is by connecting the management interface to some kind of switched infrastructure and then connecting the front-facing ports also into that switched infrastructure. At this point, we can communicate with one another because it's off the box. But without that in place, there's no way to communicate between these interfaces. From a design perspective, this can save us money in some situations. For example, I was working with an organization once that had 2 routers internal to their firewall. They had a Cisco ASA as their firewall. We had a LAN connection going between the routers and that ASA. And then the organization decided that they wanted multiple internet service providers upstream of the ASA. And in that situation, it's usually best to have a pair of routers facing the internet. Well, we had 2 perfectly good physical routers here, and rather than purchasing 2 new physical routers, we simply carved out new VRFs. We made this the internal VRF, and we created external VRFs. Those external VRFs were assigned interfaces that belonged only to the external side. At this point, we were able to connect those routers up to the ASA, we were able to connect them up to the service providers, and because the throughput requirements were nowhere near what these routers were capable of doing, we were able to save the purchase of additional hardware. So as we see here, we can get some out-of-the-box thinking out of our designs by leveraging VRFs. We don't want to go too crazy. We shouldn't just use that as our default go-to methodology of deploying layer 3 nodes into our environment, but at the same time, in some situations, it could save us from having to purchase additional hardware. So as we look at VRFs, first of all, each VRF is its own virtual routing instance. Each VRF has its own routing table. And when we're configuring VRFs, we need to assign each layer 3 interface into its own VRF. So keeping in mind that every interface by default is part of the default VRF. Lastly, there are real-world use cases. We think about service providers and we think about the management interfaces. We will see a lot of Cisco devices leveraging VRFs just from a management perspective. And lastly, again, just outside-the-box thinking as far as how we do our network designs. I hope this has been informative for you. I'd like to thank you for viewing. On the ENSLD blueprint, Cisco says that they want us to understand optimal topologies. So we're going to take what we've learned over not just this skill, but the last couple skills in the ENSLD series, and take a look at both single building and multi-building campus infrastructures. Let's take a look. Let's first take a look at a single building architecture. If we have a single building, we're not talking about large campuses. In fact, a lot of organizations out there are really running from a single location. And when we have this kind of network, we're going to find that we do not need a core. No true core block, but at the same time, we do need core routing services, which makes it so that we're going to have to adopt a collapsed core strategy, which we've talked about in previous skills. So let's look at a scenario where we have a bunch of access layer switches. It doesn't really matter how many of those that we have. And then we have a pair of switches up here that are going to aggregate all of these connections together. When we do this, what we're really doing is we're taking the distribution layer and we're collapsing the core services into it, since we don't actually have a true core layer. So this is a collapsed core and distribution layer. These access layer connections can be layer 2 or layer 3. It doesn't particularly matter for this conversation. In fact, we've talked about this in previous skills as well, whether we should make these connections layer 2 or layer 3. And again, it doesn't affect the topology. It simply affects how we go about configuring this. So now that we have our core, distribution, and access layer services accounted for, we need to think about the other network locations that we're going to deploy. For example, what about the internet? Where are we going to deploy the internet into this diagram? Well, in a lot of cases, we're going to have a firewall, and usually maybe a pair of firewalls for redundancy, or maybe an active standby configuration for that. And we're going to connect that straight into the core distribution block, and then we'll connect that up to the internet. But in some cases, we might find that we need to run BGP to the internet. Maybe we have a lot of different internet service providers. And in those cases, we're going to want edge routers that are connecting to our service providers, and then those connect into the firewalls. However we design and configure it, this is going to be our internet block. So when we talk about the hierarchical network model, for example, we look at that building block diagram. We've got the core block and distribution block here, we've got the access block down here, and we have the internet block up here. But I will go ahead and clean up this drawing so it doesn't get too busy. Next, we might want to consider the WAN block. The WAN block is going to connect all of our remote sites. So let's say we have some remote sites out here with routers that are going to connect back to this network in some fashion. So those are going to connect through a service provider. Maybe we have a pair of service providers. For now, we'll just keep this simple and say that we have one. And then this connection has to come back into our building primary location somehow. So the question is, how are we going to do this? If our service provider is able to deliver Ethernet handoffs, then in a lot of cases we can plug those straight into the core and distribution switches. However, there are two limitations that might cause us to say, you know what, instead we're going to deploy a couple of routers. The first of which might be if our service provider can't actually provide Ethernet handoffs. If we can't do Ethernet and we need to do something like a T1 or an E1 or a T3 or an E3, in those cases we have to connect those into routers anyways. However, the other big reason we might want to deploy routers would be quality of service. Because routers give us far more quality of service options, and a lot of these links out here are going to require more QoS in order to make them function properly, in order to make sure that our voice traffic survives the journey. As such, we'd bring those circuits into the two routers, and the routers would have maybe a full mesh connection here into our core and distribution block. But either way, again, we wrap all of this up into the WAN block in our hierarchical network model drawing that we're building out here. Now we have one other location that I want to consider here, and that would be where we're going to store our servers, our storage. Basically, where in the world are we going to store our applications and our data? Well, this would be the data center. And the data center is a personal passion of mine. I love data center technology. But when it comes to networking, for the most part, the data center tends to mirror what we do in the campus. In other words, we're going to have access switches that connect all of these different technologies into them. And then we have to decide, do we need a dedicated distribution layer for the data center? And inside the data center, the distribution layer takes on a different word. We call this the aggregation layer. It really means the same thing. It's just typically the aggregation layer is going to have data center specific technologies involved there. And it's a way for us to distinguish whether we're talking about the campus environment or the data center itself. So we don't call them distribution switches, we call them aggregation switches. But either way, it's the same conversation. Do we need intermediary switches between the core and distribution layer here and the data center access switches? And a lot of that's going to come down to how many access switches there are. If we only have a couple of access switches, then by all means, we can just plug those straight in. After all, we do have layer 3 services running because it's a collapsed core and distribution layer. However, if we have a lot of access switches, if we have 10, 15, 20 access layer switches, well, at that point, that's a lot of ports to consume in our core and distribution layer. And so we might want to deploy aggregation switches at that point, in which case we'd create full mesh connections upstream, and then we'd have all of our redundant connections downstream as well. But either way, this is yet another building block in our diagram. Again, the data center. Now, in some cases, the data center will be located here inside our single building. In other cases, the data center might be located outside of this building. But we've drawn this as if it's either locally configured or locally deployed, or otherwise in a building nearby that is maybe dedicated for the data center. So this is what a single building campus would look like. What happens, though, if we now have multiple buildings on our single campus? Now, there are a lot of different organizations that would fall under this category. For example, we think about higher education, universities, and colleges with all of their different buildings. Or we might think about a manufacturing facility with lots of plants located within a single geographic area. But either way, when we have multiple buildings, we're absolutely going to want to consider a true layer 3 core. So let's go ahead and draw this right in the middle of our diagram here. We'll deploy 2 switches for redundancy. And then we have to consider all of the different types of buildings that we're going to be connecting to across our campus. But the first decision that we have to make is, where are we going to deploy this core layer? Because these core switches could go into maybe our headquarters building or our IT building somewhere on campus that has significance, or in a lot of cases we might want to deploy it physically, geographically centralized. But here's the thing. In a lot of cases, this is going to come down to where in the world all of our fiber connects. Because all of our different buildings are going to be connecting back to these switches via fiber in most cases. And if we already have fiber on our campus, then wherever the fiber is pulled, that's where our core switches have to go. Now, if we're pulling new fiber, we can decide this. Well, then we have to decide again, where do we want this to go? And from a cost perspective, it probably does make sense to geographically centralize the core. So that's just a part of the conversation that we have to have when we're doing our network designs. So now let's consider a small building on campus. Let's say we have a site that has 2 different access switches. So I'll draw them out here. Chances are this is just a small, I don't know, maybe an office building. We have 5 to 10 users located there. And so we're going to take these access switches and connect them up to the different core switches. And probably we don't necessarily need a full mesh from a redundancy perspective. It just depends on the level of criticality that we have, as well as, by the way, the number of fiber connections that we have extending to all of the different buildings. In some cases, we might only have a single pair of fiber, and so we can't even do redundant connections, let alone a full mesh. Now let's take a look at a building that maybe has 6 access switches. They're a little bit larger than the last building we talked about. We could draw them out here. But what's interesting is we might have 6 total access layer switches, but maybe we could take 2 of those and turn them into a distribution and access layer switch. That means that we're going to connect down to all of the other switches in this particular building, but we're also still going to have users attaching into these switches. Then we'll connect those up to the core switches as well. Now lastly, what about a large building? Let's say maybe we have 12 access switches, or hey, we could even go larger. Maybe we have 12 different access closets, and each closet has 5 to 7 access switches in it. Either way, we're going to need true distribution switches in this case. The true distribution switches means that their entire responsibility is connecting all of these different access switches, however many there are in our building, to the rest of the network. And so we're going to facilitate connection to one another, sure, but also connection back to the core. And once again, maybe it's a full mesh, maybe it's a pair of fiber pairs, maybe it's a single fiber pair, depending on our level of restrictions. So to summarize this conversation, when we're designing each building, we need to first of all take into account the number of access layer switches. Then we need to think about whether we need true distribution switches or if we can collapse those into the access layer. And it's just going to depend on the size of the building and the number of access switches that we have. And then we need to consider redundancy. Do we have enough mission critical operations happening at this building that it warrants maybe deploying extra fiber in order to connect up at least a redundant pair, if not full mesh connectivity, to the core layer? Now, meanwhile, just like with the single building architecture that we built out, we've got to consider the other network blocks as well. For example, we're still going to likely have a data center in this scenario, and at that point we'd want to consider true aggregation switches, probably, at least maybe. Because really this conversation is still going to have to go through the same conversation we had down here at the campus layer. Because if we have a lot of access layer switches in the data center, again, for all of our servers and all of our storage, well then that makes sense for us to have an aggregation layer. If, however, we only have a pair of access switches because our data center is small, maybe we're leveraging cloud resources and so we don't have a ton of servers and storage devices stored locally, well, in that case, we probably don't need the aggregation layer. But either way, we're going to connect this up in such a way that we give servers and storage access to the network, which is going to connect back into the core layer at some level. So this would be our data center block. And once again, we're going to have our WAN block and our internet block architected very similarly, if not identically, to what we had in the previous drawing with the single building architecture. So we've built our network out. We actually see the hierarchical network model established before us with all of the different network blocks connecting into a true core layer. But at this point, we need to take the other lessons into account that we've covered throughout this skill, specifically around the idea of routing. How are we going to build our routing relationships, and what technologies can we use to optimize that? Well, first and foremost, we need to understand that in this scenario, all of these connections between core and building should be layer 3. Now, layer 3 should absolutely be the rule, but we might want to consider some exceptions. For example, this small building down here, we've got just 2 access layer switches. Does it warrant putting layer 3 switches out there just to have the benefits of layer 3? That is a conversation we're going to have to be able to have to decide whether it really does make sense to, strictly speaking, push layer 3 everywhere, even in a scenario that doesn't, technically speaking, require it. But it certainly does keep our configurations clean. For example, we are going to push our SVIs out to the distribution layer. That means our SVIs live here, they live up in the aggregation layer, they live here in this building, and yes, at this small location, we would put the SVIs on those switches. Furthermore, if we're going to deploy SVIs redundantly on a pair of switches, then we're going to want to deploy first hop redundancy protocols in order to make sure that we stay online in the event one of those switches goes down. Now, one question we might ask is, what if we collapse these distribution switches together into one device? Now we don't need FHRPs anymore because we're running a switch stack or a chassis switch. Keeping in mind that, yeah, that's a set of redundant hardware, but the software itself that's running is still a single logical switch instance. So we could still have problems there, but at the same time, whether we're deploying those technologies or VSS, maybe we deploy VSS at the core layer, well, now we've got a single logical switch and a single logical switch. Should we consider ether channeling this together? And the answer I would give in this case is no, because from a layer 3 perspective, we don't gain that much by ether channeling. So generally speaking, we do not need ether channeling in this infrastructure. Now let's conclude by talking about actual routing. So when we're talking about building routing protocol adjacencies, for example, we're going to want to make sure that we use BFD. Bidirectional forwarding detection is going to absolutely speed up convergence when we have outages in our network. And second of all, in large enterprise networks, we absolutely want to consider summarization of routes. We should be summarizing at the distribution layer towards the core layer, meaning that we restrict the number of routes that our core has to process as well as propagate throughout the rest of the network. So it's not just building the right building block architecture, both physically and logically, but we also need to take routing configuration into consideration as well. So this was quite a conversation. In fact, it was a lot of fun going through these different exercises. And I'm not going to go through a step-by-step list of takeaways because, number one, there are a lot of takeaways here that we could draw from this. But the other thing, too, is that as we've seen, there's conversation around everything when it comes to our network designs. Yes, we want to adhere as much as possible to the hierarchical network model, and so we saw that a little bit more with the campus architecture with a true core layer and distribution layers and such. But we also saw in a single building where we collapsed core and distribution. And we saw on the multi-campus side that in some cases maybe we would extend layer 2. Maybe we can collapse distribution into access layer. And so we need to make sure that we're flexible in our design principles and making sure that we don't have a hard and fast rule that we just refuse to abandon even when it makes sense, depending on the size of the network. Remember, the hierarchical network model scales all the way up to the largest networks, and that's what we like to focus on, but also scales all the way down to the smallest networks. And sometimes that small network is just the entire network. We're a small business, and our entire network is very, very little. But sometimes it's just the corner of a larger network. So like we saw on the bottom left in our drawing, that building where we only have 2 access layer switches. So that's where we have to be flexible in our network designs and make sure that while we understand the principles of what we're learning, that we're also flexible in our conversations, especially when it's not just a hard and fast decision that, yes, it's always right this way or always wrong that way. Unfortunately, for better or worse, very rarely in this field do we have those kinds of situations. Either way, it was a lot of fun going through this. I hope it was informative for you, and I'd like to thank you for viewing. We have reached the end of this skill, so let's review what we've learned by taking a quiz. First up, out of 4 questions, what are the 2 advantages to route summarization? Well, it doesn't eliminate the need for IGP timers. We did talk about BFD. That doesn't get rid of the need for timers, but it does get rid of the need to tune the timers. Summarization does reduce the size of the routing table, so that's absolutely one of our advantages. Improving BGP performance, it's not specific to any routing protocol. Better utilizing link bandwidth, it's more of a load sharing thing. We'll talk about that later on in this quiz. And lastly, absorbing network failures and changes. This is actually one of the real reasons why summarization is so important in large layer 3 domains, is to absorb the network failures. As a few different networks go down individually, we can still continue to advertise the summarized route, which means you don't have to run convergence events in our routing protocols. So B and E, these are our answers. Question number 2. An organization is concerned with link utilization across redundant links. What load sharing methodology would help make better use of secondary layer 3 connections? Well, first of all, let's just strike C and D from the record here, because source and destination hashing, whether it's IP or MAC, this is tied to ether channeling. That's usually a layer 2 concept, and while we can create layer 3 ether channels, this doesn't help us when we're load balancing between 2 different layer 3 links. So instead, we're going to be looking at our 2 primary options here, per packet and per destination. They each have their advantages, and per packet is going to give us the ability to better load balance our traffic across multiple links. So A is our answer. However, I will be very clear and say that in most cases, we don't want to actually enable per packet load balancing. We need to know the value of it and the corner case scenarios where we might want to use it. But remember that as soon as we start pushing voice over IP traffic or any type of traffic that requires in-order arrival of packets, this is going to cause all kinds of problems in our network. As such, we're usually going to rely on per destination, which is the default for Cisco platforms. It might not do as good of a job splitting our bandwidth evenly among all of our links, but it does play a large part in making sure that our traffic arrives in order at the destination. Question 3, and it's an open-ended question. Route redistribution is occurring at 2 different locations between OSPF and RIP domains. How can layer 3 loops be prevented in this scenario? Let's make a quick sketch of the scenario. We have 2 different routers in our environment that's performing redistribution between RIP and OSPF. So we have some kind of RIP domain here on the left, some kind of OSPF domain on the right, let's say. And so our concern here is that we might learn a route from OSPF, advertise it into RIP, propagate it through the RIP domain, and then redistribute it back into OSPF. This is the behavior we want to prevent. Now, there are 2 different correct answers, so either way, if you answered one of these, then you are correct. The first of which would be administrative distance. If we want to use administrative distance, then we need to make sure that one of these protocols measures external routes at a higher administrative distance value. Now, RIP doesn't actually identify any difference between external and internal routes, so this is going to fall on OSPF. So from an OSPF perspective, we'd have to leave the internal routes at 110, let's say, because that's still less than RIP at 120, but we would need to make sure that external routes are less preferred than RIP routes. And so we need to set that to at least 121, let's say, but maybe we'll go with 130 just to keep things even. Now the second answer, and probably the simpler scenario, would be to simply tag the routes. As we learn the routes from, let's say, OSPF, we could tag those as we inject them into the RIP domain, and then we would filter those tags as we try to redistribute that back into OSPF. And vice versa, by the way. As we learn things from RIP, we'll tag them, and as we try to advertise that back into RIP, we would filter it out. So if you said tagging, you're correct. If you said administrative distance, then the key there is making sure that our external routes have a higher administrative distance than any internal routes that we might learn. Okay, last question. After creating a set of VRFs, what must next be done before routes can be added into the VRF routing tables? Well, when we're thinking this through, we need to think of what the next step is after we create the VRFs. And we might recall that what we need to do after configuring the VRFs is then to assign interfaces into those VRFs. So we have to take the different layer 3 interfaces that are on this device and decide which of our VRFs they belong to. And we also need to remember that each interface can only be assigned to one VRF. We can't take one interface and assign it to 2 different VRFs, for example. That's just not going to work. So the answer here is mapping interfaces into the VRFs. And with that, this quiz is done. If you're able to identify any weaknesses in your knowledge, then be sure to go back and watch the appropriate videos in order to bolster up on that piece of information. Otherwise, congratulations on completing Design Multi-Campus Layer 3 Infrastructures. I hope this has been informative for you. I'd like to thank you for viewing.